100 years ago this month, a 36-year-old Albert Einstein stood up in front of the Prussian Academy of Sciences in Berlin to present a radical new theory of space, time, and gravity, the general theory of relativity. General relativity is unquestionably Einstein's masterpiece, a theory which reveals the workings of the universe at the grandest scales, capturing in one beautiful line of algebra everything from why apples fall from trees to the beginning of time and space. 1915 must have been an exciting year to be a physicist. Two new ideas were turning the subject on its head. One was Einstein's theory of relativity. The other was arguably even more revolutionary, quantum mechanics. A mind-meltingly strange, yet stunningly successful new way of understanding the micro-world, the world of atoms and particles. Over the last century, these two ideas have utterly transformed our understanding of the universe. It's thanks to relativity and quantum mechanics that we've learned what the universe is made from, how it began, and how it continues to evolve. 100 years on, we now find ourselves at another turning point in physics, but what's at stake now is rather different. The next few years may tell us whether we'll be able to continue to increase our understanding of nature, or whether, maybe for the first time in the history of science, we could be facing questions that we cannot answer. Not because we don't have the brains or technology, but because the laws of physics themselves forbid it. This is the essential problem. The universe is far, far too interesting. Relativity and quantum mechanics appear to suggest that the universe should be a boring place. It should be dark, lethal, and lifeless. But when we look around us, we see we live in a universe full of interesting stuff, full of stars, planets, trees, squirrels. The question is, ultimately, why does all this interesting stuff exist? Why is there something rather than nothing? This contradiction is the most pressing problem in fundamental physics, and in the next few years, we may find out whether we'll ever be able to solve it. At the heart of this problem are two numbers, two extremely dangerous numbers. These are properties of the universe that we can measure, and they're extremely dangerous because if they were different, even by a tiny bit, then the universe as we know it would not exist. The first of these numbers is associated with a discovery that was made a few kilometers from this hall at CERN, home of this machine, the largest scientific device ever built by the human race, the Large Hadron Collider. The LHC whizzes subatomic particles around a 27-kilometer ring, getting them closer and closer to the speed of light before smashing them into each other inside gigantic particle detectors. On the 4th of July 2012, physicists at CERN announced to the world that they'd spotted a new fundamental particle being created at the violent collisions at the LHC, the Higgs boson. Now, if you followed the news at the time, you'll have seen a lot of physicists getting very excited indeed, and you'll be forgiven for thinking we get that way every time we discover a new particle. Well, that is kind of true, but the Higgs boson is particularly special. We all got so excited because finding the Higgs proves the existence of a cosmic energy field. Now, you may have trouble imagining an energy field, but we've all experienced one. If you've ever held a magnet close to a piece of metal and felt a force pulling across that gap, then you felt the effect of a field. And the Higgs field is a little bit like a magnetic field, except it has a constant value everywhere. It's all around us right now. We can't see it or touch it, but if it wasn't there, we would not exist. The Higgs field gives mass to the fundamental particles that we're made from. If it wasn't there, those particles would have no mass and no atoms could form, and there would be no us. But there is something deeply mysterious about the Higgs field. Relativity and quantum mechanics tell us that it has two natural settings, a bit like a light switch. It should either be off, so that it has a zero value everywhere in space, or it should be on, so that it has an absolutely enormous value. In both of these scenarios, atoms could not exist, and therefore all the other interesting stuff that we see around us in the universe would not exist. In reality, the Higgs field is just slightly on. Not zero, but 10,000 trillion times weaker than its fully on value, a bit like a light switch that's got stuck just before the off position. And this value is crucial. If it were a tiny bit different, then there would be no physical structure in the universe. So this is the first of our dangerous numbers, the strength of the Higgs field. Theorists have spent decades trying to understand why it has this very peculiarly fine-tuned number, and they've come up with a number of possible explanations. They have sexy-sounding names like supersymmetry or large extra dimensions. I'm not going to go into the details of these ideas right now, but the key point is this. If any of them explain this weirdly fine-tuned value of the Higgs field, then we should see new particles being created at the LHC along with the Higgs boson. So far, though, we've not seen any sign of them. But there's actually an even worse example of this kind of fine-tuning of a dangerous number, and this time it comes from the other end of the scale, from studying the universe at vast distances. One of the most important consequences of Einstein's general theory of relativity was the discovery that the universe began as a rapid expansion of space and time 13.8 billion years ago, the Big Bang. Now, according to early versions of the Big Bang theory, the universe has been expanding ever since, with gravity gradually putting the brakes on that expansion. But in 1998, astronomers made the stunning discovery that the expansion of the universe is actually speeding up. The universe is getting bigger and bigger, faster and faster, driven by a mysterious repulsive force called dark energy. Now, whenever you hear the word dark in physics, you should get very suspicious, because it probably means we don't know what we're talking about. We don't know what dark energy is, but the best idea is that it's the energy of empty space itself, the energy of the vacuum. Now, if you use good old quantum mechanics to work out how strong dark energy should be, you get an absolutely astonishing result. You find that dark energy should be 10 to the power of 120 times stronger than the value we observe from astronomy. That's 1 with 120 zeros after it. This is a number so mind-bogglingly huge that it's impossible to get your head around. We often use the word astronomical when we're talking about big numbers. Well, even that won't do here. This number is bigger than any number in astronomy. It's 1,000 trillion times bigger than the number of atoms in the entire universe. So that's a pretty bad prediction. In fact, it's been called the worst prediction in physics. And this is more than just a theoretical curiosity. If dark energy were anywhere near this strong, then the universe would have been torn apart. Stars and galaxies could not form, and we would not be here. So this is the second of those dangerous numbers, the strength of dark energy. And explaining it requires an even more fantastic level of fine-tuning than we saw for the Higgs field. But unlike the Higgs field, this number has no known explanation. The hope was that a complete combination of Einstein's general theory of relativity, which is the theory of the universe at grand scales, with quantum mechanics, the theory of the universe at the small scales, might provide a solution. Einstein himself spent most of his later years on a futile search for a unified theory of physics, and physicists have kept at it ever since. One of the most promising candidates for a unified theory is string theory. And the essential idea is, if you could zoom in on the fundamental particles that make up our world, you'd see actually that they're not particles at all, but tiny vibrating strings of energy, with each frequency of vibration corresponding to a different particle, a bit like musical notes on a guitar string. So it's a rather elegant, almost poetic way of looking at the world, but it has one catastrophic problem. It turns out that string theory isn't one theory at all, but a whole collection of theories. It's been estimated, in fact, that there are 10 to the 500 different versions of string theory. Each one would describe a different universe with different laws of physics. Now, critics say this makes string theory unscientific. You can't disprove the theory. But others actually turned this on its head and said, well, maybe this apparent failure is string theory's greatest triumph. What if all of these 10 to the 500 different possible universes actually exist out there somewhere in some grand multiverse? Suddenly, we can understand the weirdly fine-tuned values of these two dangerous numbers. In most of the multiverse, dark energy is so strong that the universe gets torn apart, or the Higgs field is so weak that no atoms can form. We live in one of the places in the multiverse where the two numbers are just right. We live in a Goldilocks universe. Now, this idea is extremely controversial, and it's easy to see why. If we follow this line of thinking, then we will never be able to answer the question, why is there something rather than nothing? In most of the multiverse, there is nothing, and we live in one of the few places where the laws of physics allow there to be something. Even worse, we can't test the idea of the multiverse. We can't access these other universes, so there's no way of knowing whether they're there or not. So we're in an extremely frustrating position. That doesn't mean the multiverse doesn't exist. There are other planets, other stars, other galaxies, so why not other universes? The problem is, it's unlikely we'll ever know for sure. Now, the idea of the multiverse has been around for a while, but in the last few years, we've started to get the first solid hints that this line of reasoning may get borne out. Despite high hopes for the first run of the LHC, what we were looking for there, we were looking for new theories of physics, supersymmetry, or large extra dimensions that could explain this weirdly fine-tuned value of the Higgs field. But despite high hopes, the LHC revealed a barren subatomic wilderness populated only by a lonely Higgs boson. My experiment published paper after paper where we glumly had to conclude that we saw no signs of new physics. The stakes now could not be higher. This summer, the LHC began its second phase of operation with an energy almost double what we achieved in the first run. What particle physicists are all desperately hoping for are signs of new particles, micro black holes, or maybe something totally unexpected emerging from the violent collisions at the Large Hadron Collider. If so, then we can continue this long journey that began 100 years ago with Albert Einstein towards an ever deeper understanding of the laws of nature. But if in 2 or 3 years' time, when the LHC switches off again for a second-long shutdown, we found nothing but the Higgs boson, then we may be entering a new era in physics. An era where there are weird features of the universe that we cannot explain. An era where we have hints that we live in a multiverse that lies frustratingly forever beyond our reach. An era where we will never be able to answer the question, why is there something rather than nothing? Thank you.
Harry, even if you just said the science may not have some answers, I would like to ask you a couple of questions. And the first is, building something like the LHC is a generational project. I just mentioned introducing you that we live in a short-term kind of world. How do you think so long-term, projecting yourself out a generation when building something like this?
Yeah, I mean, I was very lucky that I joined the experiment I work on at the LHC in 2008, just as we were switching on. And there are people in my research group who've been working on it for 3 decades, their entire careers on one machine. So I think the first conversations about the LHC were in 1976. And you kind of start planning the machine without the technology that you know you're going to need to be able to build it. So the computing power did not exist in the early 90s when design work began in earnest. One of the big detectors which record these collisions, they didn't think there was technology that could withstand the radiation that would be created at the LHC. So there was basically a lump of lead in the middle of this object with some detectors around the outside. But subsequently, we have developed technology. So you have to rely on people's ingenuity that they will solve the problems, but it may be a decade or more down the line.
Now, China just announced 2 or 3 weeks ago that they intend to build a super collider twice the size of the LHC. I was wondering how you and your colleagues welcome the news.
Well, size isn't everything, Bruno.
I'm sure. I'm totally sure of that.
It sounds funny for a particle physicist to say that. But I mean, no, seriously, it's great news. So building a machine like the LHC requires countries from all over the world to pool their resources. No one nation can afford to build a machine this large, well, apart from maybe China, because they can mobilize huge amounts of resources, manpower, and money to build machines like this. So it's only a good thing. What they're really planning to do is to build a machine that will study the Higgs boson in detail and could give us some clues to whether these new ideas, like supersymmetry, are really out there. So it's great news for physics, I think.
Harry, thank you.
Thank you very much.